So, welcome back student to the next class of complex analysis. In the previous class, we started something which called power series. A series can be represented in this way, which we call power series, and then find the radius of convergence of this particular series. Radius of convergence is defined as 1 by L. R is equal to, where L is limit k tends to infinity a k plus 1 by a k. So, we are normally using this ratio test, but today I will going to show just doing the next thing. Before going to the next topic, I just show one thing, that this L can also be find out with root using the root test. And sometimes if the coefficient of A is such that it is difficult to find out the ratio test, then we may go to this root test also. So, let me show you one example where maybe it will be easier to find out the root rather doing the. So, just one example. So, as a continuation of the previous lecture, so I have something 5k plus 1 divided by 2k, say 3k plus 2 whole to the power of k, and then multiplied by z minus 3i k. So, this is the problem that is given to us, where I have something like this. So, now if you check what is your a k, it is straightforward that it will be 5k plus 1 divided by 3k plus 2 whole to the power k. But what is your a k plus 1? It will be 5k plus 1 plus 1 divided by 3 k plus 1 plus 2 whole to the power of k plus 1. So, now when you try to find out what is your a k divided by a k plus 1 divided by a k, then there is some problem, because this will not cut, the cancellation will be not that easy, and then you need to take the limit, it will not be that simple. But if you take the root of that, then things will be simpler. So, if I want to take the value this with this test k tends to infinity a k, then mod of this to the power k is simply comes out to be limit k tends to infinity this quantity 5k plus 1 divided by 3k plus 2. So, now things are done. So, you have this quantity. So, now if I put the limit, then limit k tends to infinity, this will be, if I take k common out, then it will be 5 plus 1 by k divided by 3 plus 2 by k, and if I put k tends to infinity, then this term will going to vanish, and finally we will have something 5 by 3. L become 5 by 3, R which is 1 by L will be 3 by 5. So, here 3 by 5 is my radius of convergence, and the way we do in the previous case, the previous problems, here also we can find. So, 3i is somewhere here. If I make a circle around 3i whose radius is 3 by 5 say, something like this, then these are the region of z for which it will going to converge. Okay. So, this is one example where you can use the root test rather ratio test, just to show that in some problems you may need to apply the root test also. It is not necessarily always you will going to apply the ratio test. Ratio test is convenient. The way problems are given, normally we start with the ratio test, but it is not necessarily that always you use the ratio test. Root test is another way to do that. Okay, so next in our syllabus we will have something interesting, which is called the Taylor series of complex function. Taylor series. Let me just state quickly. So, what is the meaning of this Taylor series? All of you are aware of. So, if a function f z is analytic in some domain, D. So, that means if I have some domain here D, it is analytic, then f z can be expanded as power series around some point z0 like this, no problem with that so far. So, we have some point z0 here, around this point I can expand this function. F z is analytic in the domain D, I have a z0 point, I can expand these things around that point, where ak, now ak is a coefficient which is a characteristic coefficient. So, this characteristic coefficient will be this. So, the characteristic coefficient can be represented in this way. So, in total I can write that the function f z can be represented like this. This is the statement of the Fourier series, whatever the Fourier series we have. So, a function which is analytic in some domain D, I can expand that particular function around some point z0, and if I expand this function around the point z0, then I have some ak, this characteristic coefficient in my hand, and this characteristic coefficient will be something like this, where the function derived k time ak is the k time derivative at that particular point divided by factorial. Here it should be factorial k, I should not use n here, factorial k and this. Okay, so quickly try to understand how these things is happening. So, if I have some point say z here and this radius says I, so inside that I am expanding. So, z is the point inside this region. Then I have, so let me first write the Cauchy's integral formula, because I am going to use that. The Cauchy's integral formula suggests this is 1 by 2 pi I xi minus this, where I write xi, which is variable here. It is, I should write this at z. Yeah, I write the Cauchy's integral formula in a different way. I write fz in terms of xi here. Normally, if you remember that it was something like fa was 1 by 2 pi I integration of z divided by z minus a dz. This index I just changed to xi and this a I changed to z. So, z is a point here where try to find out the value of the function, and xi is the region having a circle say, and I just change that. So, the thing will not going to change, the things is same. So, fn z is 1 by 2 pi I with factorial n here sitting xi minus z whole to the power n plus 1 d xi. These two expression I have from this Cauchy's integral formulas. This is a very important expressions I mentioned earlier. So, these two I have in my hand. So, let us try to exploit these two expression and check whether I can have these things or not. So, if I expand, for example, xi z, I write these things in terms of z0 because around the z0 I trying to expand my function. Remember, this is my function fz, right hand side is something, and I am trying to expand this function around z0. So, somehow the z0 point should come here. So, let me write this as xi minus z0 minus z minus z0, this. So, minus z0 and plus z0 I add, and I rewrite this same expression in terms of z0, so that the z0 terms will cancel out. So, that just xi and z is sitting here. Now, what I will do, that I will take xi minus z0 common out of here, and I will have an expression z minus z0 divided by xi minus z0 whole to the power minus 1. Again I rewrite the same expression in a different way. I take this common outside, then it will be 1 minus z minus z0 divided by xi by z0, and this xi by z0 1 minus z by z0 divided by xi by z0, I can take it, write it in this way with to the power minus 1. Now, if we now expand this quantity, so it will be something like 1 plus xi minus z minus z0 xi z0 cube and so on. Also, one thing we should note that z minus z0 is this and xi minus z0 is this. So, z is inside. So, z minus z0 divided by xi minus xi0, if I take the mod out of that, it should be less than 1, because this quantity is less than this quantity. So, it will be just less than 1. then I have the ability to expand this in this way, this power series. Now 1 by z is expanded in this way, and I can put this here. So my fz is something 1 by 2 pi I closed integral xi by xi minus z0 multiplied by 1 plus z minus z0 divided by xi minus xi0 plus z minus z0 square divided by xi minus square, and so on with d xi. I just replace this 1 by xi, this quantity here, and as a result I have an expansion of fz in terms of this. This is the thing. Okay, so let me erase this part. Maybe I shouldn't require this also. Then my fz, first term, if I calculate, it is 1 by 2 pi I, then integration of xi by xi minus z0 d xi. This is my first term. What is my second term? Plus 1 by 2 pi I integration of, please note that z minus z0 square, all things are not a function of xi. So, I can take it outside. It is, so here it will be z minus z0, that is going to outside, then xi divided by xi minus z0 square. This is my second term. What about the third term? Third term will be z minus z0 square divided by 2 pi I, total integration of xi divided by xi minus z0 cube d xi, and so on and so on. Now, what I will do, I will just try to find out what is the meaning of this term. This term, if I look here, it is nothing but fz. The first term is nothing but f at z0, the first term. Second term is how much? Z minus z0 multiplied by f prime at z0, because this quantity 1 by 2 pi xi integration of xi minus z0 square is nothing but f prime z0. What about the third term? Third term is z minus z0 f double prime z0 divided by factorial 2. I need to put a factorial 2 because this term will come here. So, if I check from here, so factorial 2 is 1 by 2 pi I integration of the rest. So, I am taking this term where n is equal to 1, n is equal to 2. So, that means cube term will be here. So, here we have the cube term. So, here we have a square term, by the way. And I should have a factorial 3 here, factorial 2 here. So, that means if I go on with this, So, I will eventually have this quantity if nth order derivative or if kth order derivative z0 divided by factorial k z minus z0 whole to the power k, which is nothing but by the Taylor series expansion that the first expression that I have written. So, this. So, we can know that how to calculate the Taylor series, at least an idea that how this Taylor series is expanded with the fact that if a region is given to me, I can expand my Taylor series in this way. Okay. So, after having a very rough idea how the Taylor series, we prove the Taylor series is defined in this way. Let us go back to some problems, because at the end of the day you need to do few problems, and when you do the problems you need to be careful enough to expand. Before that, so let me again write just the expression of the Taylor series. So, Taylor series suggests if a function is analytic in some region G, then it can be represented in the power series in this way, where AK is defined like this, factorial k. This is the expression of the Taylor series. Now, if z0 is a point around which I try to expand my function, if this point z0 is equal to 0, if this function z0 equal to 0, this function is now represented like AK, let me write total. So, f k at 0 factorial k z to the power k. The same function is now represented in this way, since I put z0 is equal to 0, because z0 is the point around which I try to expand my function, but I put z0 point is 0. If I do that, then I have another expression. So, this is called the Maclaurin series. So, that means if the Taylor series is, if I expand a function in terms of Taylor series, if this z0 point is equal to 0, then that series is nothing but a Maclaurin series. So, Maclaurin series is a special case of Taylor series where this point z0 is taken at 0. Okay. After this Maclaurin series and Taylor series, now we are in a position to do some problem, as I mentioned. So, let us try to find out some example. So, example is function f z is equal to 1 by 1 minus z. This is a function. Now, the question is asked that please expand this function around this point z0 is equal to 1. Around this point I need to expand this function. So, now the process is straightforward. We do not need to. So, there are two ways you can do that. You can write straightway this function in this form. z0 is given to you. So, that means this is I. So, AK, how do I find? AK, you can just make a derivative. The function is given. So, you just make a derivative of this function first, second, third or fourth and n time. So, you have a general expression of the derivative and put this value at I and factorial k divided. So, this is the standard way to do the calculation, but apart from that you can do in different way also. The way I prove the Taylor series, I will use the same logic here, the same thing. So, the point is somewhere here around which I need to expand my function. So, this is point I. So, f z is 1 minus z, I will add this I and subtract this I like this, and then what I do, I will write 1 minus I minus z minus I, this. Then I will do 1 minus I common, then it will be just 1 minus z minus I divided by 1 minus I minus 1, right. So, this expansion, whatever the expansion I will have, is simply the Taylor series expansion. So, if I do, then it will be 1 minus I 1 plus z minus I 1 minus I plus z minus I whole square 1 minus I whole square, so on. So, I already have a series expansion for a given function around the point z equal to 1. So, what is the general form? Let me erase this part. What is the general form I have? The general form is, in the summation form, is summation z minus I k divided by 1 minus I k plus 1. So, this is the expansion I will have. So, k from 0 to infinity, this is the expansion I have. Now, it is equivalent to the power series, as I mentioned. That means, I can now find what is my AK. AK is 1 divided by 1 minus I whole to the power of, say, k plus 1. This is my AK. So, now once I have a AK, so next thing is that I can expand this function around point z0 equal to y, that is true. But I need to know the radius of convergence also, because I can't expand this to entire region. There is a restricted region along which I can expand this in terms of Taylor series, that is the point. So, once I have AK, I can readily find out what is my L, which is limit k tends to infinity mod of a k plus 1 divided by AK, which is a k plus 1 by AK means limit k tends to infinity 1 by 1 minus I, this quantity. A k plus 1, if I put, it will be k plus 2, and a k will be k plus 1 in the upstairs. So, in the denominator we have just 1 by 1 minus I. Once you have that, you can have the value of L. Since it is a mod, so k is not important here, because k is not there at all. So, 1 minus plus I divided by 1 minus I 1 plus I. So, this quantity is how much? 1 plus I, and this is divided by a square plus b square. So, it is 2. Mod of this quantity is 1 by 2 square plus 1 by 2 square whole to the power half. So, it is just 1 by root 2, right. 1 by 2 square is 1 by 4 plus 1 by 4. So, 1 by 4 is 2 by 4. So, half. So, 1 by root 2. So, what is my radius of convergence here? R, original function I should write here. R, radius of convergence, is 1 by L is equal to root over of 2. That means this is 1. If I have a circle like this where this radius is root over of 2, then in this region this Taylor series is valid, because I can expand the Taylor series, but I should keep in that mind that my radius of convergence is also there and the radius of convergence is root 2. So, whatever the value of z is here, for that z I can expand the Taylor series the way I expanded. So, okay student, I would like to stop my class here. In the next class we will go to few other problems related to the Taylor series. We will another 2-3 problems and then go to something interesting which is called the singularity. Before going to the next step, today we will learn Taylor series. In the next class, maybe in the next to next class, we will learn another important, very important series called Laurent series. But before going to learn the Laurent series, we need to learn more about the singularity. We have a rough idea about that. So, in the next class, we will do few more problems related to the Taylor series expansion and try to learn the meaning of the singularity and different kind of singularity. With this note, so let me conclude the class here. Thank you for your attention.